The greatest mathematical invention in the 1600s was integral calculus. This tool not only allowed the solution of many previously unsolvable problems, but it also made quick work of many laborious processes in math. Hi, my name is Tom Atwater, and in today's lesson, we will be investigating the definite integral. In this section, we move from finite sums to infinite sums, and we'll look at some applications of them. But let's start by setting up some notation, sigma notation. The Greek letter, capital letter, sigma, stands for the sum. The index k tells us where to begin the sum, and k, as you can see, is underneath the sigma. And where to end the sum, we find the number above sigma. And if infinity happens to be the symbol that's above sigma, where I have my n right now, then it indicates that the terms go on indefinitely. However, we do have an n on this one, and so this is a finite sum. We use sigma notation to write the sum of the area of an infinite number of rectangles between the graph of the curve and the x-axis. Let's take a look at that definition right now for the definite integral as a limit of Riemann sums. Let f be a function defined on a closed interval a comma b. For any partition p of the interval ab, let the numbers ck be chosen arbitrarily in the subintervals x sub k minus 1 comma x sub k. If there exists a number I such that the limit as p goes to 0 of the summation of f of c sub k times delta x sub k is equal to I, no matter how p and the c sub k's are chosen, then f is an integrable function on the closed interval a comma b. And I is the definite integral of f over that closed interval a comma b. Let's look at a diagram to help us and illustrate what this definition is saying. So here I have two different graphs that are of the same curve, and we're looking at the area formed by the curve and the x-axis. So what you can see here on this side is that we've divided up into these partitions. And over here, we've divided up into partitions. And the red lines are those partitions we're looking at. And as we've seen before, we're looking at the midpoint of these partitions. And the same thing here, looking at the midpoints of the partitions. And these rectangles are approximating the area under the curve. On the right-hand side, you can see that what we've done is actually divided them into a different set of partitions. These partitions there's more of them, and therefore each one makes a better estimate of that area. And the colors here represent the fact that when we look at this area, it's actually going to turn out to give us a negative result. And when we look at the area on the bluer section, that will give us a positive area. So it is possible that when we do some of these integrations like this, that we will get a net area that's negative. Another conclusion to make about a continuous function is made in the following theorem. So let's take a look. The existence of a definite integral. All continuous functions are integrable. That is, if a function f is continuous on the interval a comma b, the closed interval a comma b, then its definite integral, the definite integral over the a comma b exists. Now, we need to set up some notation for the integrals. And so what we have is this. we have an integral sign, which is right here, and it looks sort of like a stretched out S. We have the lower limit and upper limits of the integrals that we're interested in. So those are our intervals, the upper and lower limits. Inside of the integral is our integrand. The variable over which we are doing the integration is right here. In particular, it's x. And we're saying that this is differentiated over x. Then we can see that the whole thing is the integral from a to b. And I talked about a and b as the lower and upper limits. And finally, the way you read this is the integral from a to b of f of x dx. And when you find the value of the integral, then you have evaluated the integral itself. Okay, now, let's work with this notation, which is to say, let's take this particular example and express the limit as a definite integral. So when we look at this, we can see that we are given my lower and upper limits. 0 would be my lower limit. So as an integral, I'm going to put 0 down here. And my upper limit would go up there. Now, as I look at what is happening in the function, this is the general function of we're squaring whatever the term is that we have. In other words, it's x squared. And so we need to put in the fact that we're integrating over the variable x, and that's the dx that I've added in there. So that would be my definite integral for that particular Riemann sum. Now, the second example, it's very similar in that here is my lower limit, and that's my upper limit. So I have from 0 to 1. Now, when I look in here, what's happening in terms of a function is we are taking the square root of 4 minus the element. And the element can be, of course, anything. And in this case, we're using x. So it would be the square root of 4 minus x squared. And that's my integrand. So I put that right here, square root of 4 minus x squared. And then I need to tell it over what variable that we're integrating. And so that would be dx. So those are both examples of how we can use the definite integral as the changing from the sigma notation to the definite integral notation. All right, we have some examples to do, and we've been approximating the area between a function and the x-axis so far with finite sums. Well, now we can do the same with infinite sums and use the integral. Let's take a look at the definition for the area under a curve as a definite integral. If y equals f of x is non-negative and integrable over a closed interval a comma b, then the area under the curve y equals f of x from a to b is the integral of f from a to b and is notated as the area under the curve a equals the integral from a to b of f of x dx. All right, so now what we can do is actually try some examples where we're going to use that notation. So here we have used the graph of the integrand and areas to evaluate the following integral. And the integral we have is the integral from -3 to 3 of the square root of 9 minus x squared dx. We were told to use the graph of this, which of course is the graph, the upper half of the circle. So what we're looking for is the area of this semicircle. We know that this endpoint is negative 3, and we know this endpoint is 3, which means we know that the radius is 3. So to find the area of a circle, it's pi r squared. So that means the area of a semicircle is half of that. So the area is 1/2 pi r squared, but r here is 3, so 3 squared. Work that out and we get 9 pi over 2. Well, what does that actually mean? What it means is that if I take my definite integral, which was negative 3 up to 3 of the square root of 9 minus x squared dx, that's going to equal 9 pi over 2. So that gives me the evaluation of the integral, and the evaluation of that integral is the area underneath its curve. Let's try another example where we're going to look at the graph and use that to help us evaluate the integral. So we're going to take this time to use the graph of the integrand and the areas to evaluate this particular integral. The integral from negative 1 to 1 of 2 minus the absolute value of x dx. Well, you might recognize that's an absolute value function, and something's going to happen because we have this minus sign in front of it. And so let's take a look at what that graph looks like. And that graph looks like this. We have obviously what's happened to the absolute value function because of the negative side is that it's been rotated about the x-axis, so it's essentially upside down from what we normally think of. Now, what we have going on is the interval is from negative 1, which is right here, to positive 1, which is right here. Well, closely right there. And so what we really have is that this is really a trapezoid on its side, right? Where this would be considered one of the bases, and this would be considered the other base. And so in particular, this length right here, we could say would be the height of it, but it just happens to be lying on its side instead. Well, the area for a trapezoid, you'll remember, is the bases, the average of the bases times the height. And if we look at what we have going on here, the way that the graph was drawn, this is 1 here for the y value. And so in terms of base 1, it's actually 2. So the scale is a little bit off, but you can see the demarcations that we have an area which is base 1, which I've called this 2, plus base 2, which is at a height of 1, over 2 times, and then the height, even though it looks longer, the height is only 1. So when I multiply all of this together, I get 3/2 for the area of this one trapezoid. However, there are 2 trapezoids, and this one is a mirror image of the other trapezoid. Therefore, we have 2 trapezoids with each having an area of 3/2, so the area of that entire curve is 3. Well, once again, what does that tell us about the definite integral? What it tells us is that the definite integral from negative 1 to 1 of 2 minus the absolute value of x dx is equal to 3. And that's how that can help us in terms of finding the definite integral as looking at it as the area underneath the curves. All right, remember that when we're finding the area and we want to evaluate the integral, that if we notice that sometimes we might have negative areas, and we need to keep that in mind. But first, let me look at how we integrate a constant function. And so the way we do that is by this theorem for the integral of a constant function. if f of x is equal to c, where c is a constant on the closed interval a comma b, then the integral from a to b of f of x dx is equal to the integral from a to b of c dx, which is equal to c times b minus a. Well, in this particular case, what I want you to understand about it is that we are finding the area of a rectangle, because if we draw the graph of a constant function, it's a straight horizontal line. And if we're going from A to B, and I'm just saying arbitrarily where they might be, then we are looking for this area, the area of the rectangle under that constant function. Well, let's try this out with an example. Let's evaluate the integral from 0 to 3 of negative 160 dt. And so we use the formula that we just looked at, which tells us that the integral from 0 to 3 of negative 160 dt is equal to the constant negative 160, times the difference in the interval b minus a, which is 3 minus 0, so that's equal to negative 480. And so that's how we can use that formula to find the integral, or the definite integral, of a constant. Now, some discontinuous functions are integrable. And so we're going to look at an example of a discontinuous function, but that we can find the integral for. So find the points of discontinuity of the integrand on the interval of integration. Use the area to evaluate the integral. And what we have here is the integral from negative 1 to 2 of the absolute value of x divided by x dx. Here's the graph. Let's examine this. We have this line here, which is spanning a distance on the x-axis of 2 and on the y-axis of 1. Once again, the scales are different, but they are clearly marked. On the left-hand side, we have also a distance unit of 1 and for x, and as well for y. So what we really are looking for is the area of this rectangle, which is 2 times 1, or in other words, it's equal to 2. And the area of this one, we're going to say is negative 1 because it's below the curve. So that when we look at the net area, and it's important to use that word net area because that implies that we're allowing the possibility of negative areas. The net area is, well, 2 plus minus 1, which is, of course, equal to 1. How does that help us in terms of the definite integral? Once again, we can write down the definite integral from negative 1 up to 2 of the function absolute value of x over x dx is going to be equal to 1. So that's an example of where we allowed for a negative area and calculated the net area. Well, now it's time for you to try a problem. And the problem that I would like you to do is similar to what I did. That is, I want you to find the points of discontinuity of the integrand over the interval of integration. Then use the area to evaluate the integral. Let me give you a hint that you might want to look at the possibility of simplifying that before you draw its graph to help you to solve the integral part of it. So you have the integral from negative 3 to 4 of x squared minus 1 over x plus 1 dx. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Welcome back. Well, I hope you found that when you looked at the simplifying this, that you would get this graph. However, I hope you also realize that with the x plus 1 in the denominator, that gives us a point of discontinuity at x equals -1. So at x equals -1, we would have an open circle as part of the graph. So it is discontinuous at that particular point. However, that doesn't affect the fact that we still have a right trapezoid, I'm sorry, I made a mistake, a right triangle, which we can find the area of, because we can still, even though there's a hole there, realize that we can draw that side of the triangle. And then over here, we have another right triangle of which we can find the area. So let's go about doing that. What we have is, in the triangle on the right, the base is 3. That was strange. There we go. The base is 3, and the height also happens to be 3. And let me draw that 3 again. Okay. So the area for that triangle is 1/2 base times height. So it would be 1/2 3 times 3, or in other words, 9 halves. Well, what about the area over here? The area of this triangle is 1/2, and this time we have 4 as what I will refer to as the base, even though it's upside down, and the side is also 4 units. And again, the scale isn't quite accurate, but you can clearly see the demarcations of the x and y axes. So therefore, this is going to be equal to 1/2 of 4 times 4, but it's underneath the x-axis, which gives us a negative result for -8. So now when we want to find the net area, it's going to be -8 plus 9 halves, which works out to be -7 halves. How did that help us with the integral itself? Well, we know that we were integrating from -3 to 4, the function x squared minus 1 over x plus 1 dx. And so that will have an area or a value of the integral of -7 halves. So that's the answer you should have gotten on that pause video problem. Good job today. So in this lesson, we explored the definite integral as a means for finding or being evaluated by finding the area under the curve and the x-axis. Be sure to work the exercises that your teacher assigns, and we'll see you next time.